Bismillahirrahmanirrahim. Assalamu alaikum. Dear students of CS352 Introduction to Soft Computing, welcome to lecture 9, section 9.3, where I'll be talking about fuzzy inference processing and fuzzy systems in the control systems and AI, fuzzy logic. Just a bit of a recap. In section 9.1, I had introduced the concept of fuzzy logic and control systems and AI. In section 9.2, I talked about the basic mathematics underlying the fuzzy systems and fuzzy logic processing, where we talked about the difference between fuzzy sets and classic sets and what is the difference between the fuzzy systems and the classical logic based systems. In today's lecture, we'll be talking about fuzzy inference processing, and we'll be trying to build up two systems specifically for fuzzy inference processing and try to see the different components that are interesting for fuzzy inference. Then in the next lecture, I'll be talking about a specific application, taking up a room cooler in mind and building up a fuzzy logic based system. So without further ado, let's begin with lecture on fuzzy inference processing. So here is the agenda for section 9.3. We'll be starting with the concept of fuzzy inference processing, where I'll be introducing the three main models for fuzzy processing. Then we'll see a small case study of how a fuzzy inference is processed and the major components. We'll then move on to study the fuzzy inference systems, followed by fuzzy logic control systems. After seeing the characteristics and properties of fuzzy inference systems, we'll then talk about the characteristics and assumptions of fuzzy logic control systems. We'll see the major components of FLCs. We'll then talk about the different steps in designing FLCs, and then we'll basically be seeing fuzziness in neural networks and how does that work, which will then be followed by a quick summary or key points that we have studied in this lecture. Before we start with fuzzy logic based systems and fuzzy logic control systems, I think it is necessary that we talk about fuzzy inference processing. So the basic concept here is, how do we represent fuzziness, how do we express the parts of fuzzy rules, and how do we express fuzzy values. So to do that, we need to define the models through which we can define a particular value for a given input. So let us suppose that we have got an xi, which is our input, and y is the consequent output in fuzzy rules. So then we basically have got three rules which can relate this value y to our input values xi. And these three models for fuzzy processing are based on the expression of consequent parts in the fuzzy rules. For example, the first one, as shown here, is the Mamdani fuzzy inference processing, or the Mamdani model of fuzzy inference processing. And according to this model, we'll always have a fuzzy number to reflect fuzziness. So for each input, the output is always a fuzzy value, a fixed constant value a, which reflects the fuzziness of the input. The second model for fuzzy processing is basically called Takagi Sugano Kang, or TSK model, which just states that you have got basically the first input variable a0 followed by the other input variables, and the output is just the weighted linear combination of input variables. So I can represent that as y is equal to a0 plus the sum of ai xi, and that is just the a's here are basically the weights, and xi is the input as defined in the previous point. Finally, the third model is a simplified model for fuzzy processing, which just says that again, for any value of the input, the answer is just the constant. All of these three are used for fuzzy inference processing, but usually the Mamdani model is the most common one, followed by as well for if you've got multiple features, then a lot of times the TSK model is also used. But to sum it up, I think all three models are equally useful and should be studied at least at the theoretical level. So let us take a small case study just to kind of let you know a little bit more about what is important in fuzzy logic and why do we use fuzzy logic. So in this case study, we want to control the speed of a motor in a room cooler. According to the problem, a room cooler has a fan encased in a box with a evaporative pad, wool or hay. In our common terms, we call it the Lahori coolers. But the basic physics that works is that it uses evaporative cooling. That is, when the water evaporates, it basically leaves it absorbs some temperature, it absorbs some heat, and then the temperature is lowered for the air, and the air becomes cool, and with that cool air it is pumped out into the room to cool the room as well. And the evaporative pad or the wool is continuously moistened by water, so that when the water evaporates, it absorbs some heat and leaves the air cooled. And this water is flown through a pump that is connected to a motor. So you basically fill the cooler with water, and that water is pumped up, and then basically it's blown down through the evaporative pad, whether wool or hay. Of course, the rate of flow of water is to be determined. That's our main purpose. The more water you have, of course, the more water that flows down, probably it's going to cool more. But you want to maintain a room temperature, and hence the rate of flow of water will be directly dependent on the function of room temperature and the speed of fan. So for us, there are three important characteristics here. The first is the rate of flow of water. The second, the rate of flow of water is your output value that we want to determine. The second important parameter here is the function of room temperature. So room temperature is our second parameter, and similarly the speed of fan is going to be your third parameter. Room temperature and speed of fan combined gives you the output of the amount of water that is to be pumped. On the other hand, the speed of the motor will be dependent on two parameters, temperature and humidity, but these are both dependent, because if you increase the humidity, then you are going to reduce the temperature. So for us, you need to keep in mind the important characteristics are the rate of flow of water, the room temperature, and the speed of fan. To summarize what I said earlier in the previous slide, it's the same thing again. You've got two input variables, one is the room temperature and the other is the cooler fan speed. The output variable is basically the flow rate of the water, and we need to define the fuzzy regions using fuzzy terms. And to do that, I'll just kind of mention the fuzzy terms and the variable names, so that you're kind of comfortable with them and you understand what I mean by fuzzy. So for example, the temperature can be either cold, cool, moderate, warm, or hot. So it can take any of these values. That's a set that is defined, the fuzzy set that is defined for temperature. It can either be cold, cool, moderate, warm, or hot. Similarly, for the fan speed, which is measured in rotations per minute, you can either be slack, low, medium, brisk, or fast. And finally, the output value or output variable, which is called flow rate of parameter, flow rate of water, that is going to be strong, negative, negative, low negative, medium, low positive, positive, and high positive. And in this way, we can kind of define our variables in terms of fuzzy terms. Of course, we need to define the fuzzy terms with respect to their membership functions, and the membership functions will need to be specifically defined using graphs and quoted here. So in this particular case, for this room cooler, we are going to define the membership functions of each parameter. For example, if the temperature is between 1 degree and 10 degree, it's going to be cold. But the membership values of cold will vary depending on the higher the temperature, the lower the membership value. And this is shown by this particular graph. The first graph that you see on the left hand side, we see that the cold value is between 1, has a membership value of 1 and 0, and it is varying between for temperature between 1 degree and 10 degree. Similarly, the value cool is again varying for the membership value is again varying for cool, and it has to be, if the temperature is between 7 degree and 22 degree, it can be cool up to a certain membership value, function value. Similarly for moderate, for warm and hot. Similarly for motor speed, we can also assign membership values to slack, low, medium, brisk and fast. And finally, it's the same process, same membership values are assigned to their respective values for each parameter, each of the 3 parameters, for the flow rate as well, which is in milliliters per second. And here what we see is that the maximum value, the maximum degree of membership of each particular value for a variable, it's 1, and the minimum value is 0. And we can see that we can identify, for example, that if the temperature is, let's say, 21 degree, then the fuzzy terms that we can assign to this temperature is that it's moderate up to a specific value, let's say 0.2, and it is cool with the membership value of 0.2, while it cannot be warm and it cannot be hot and it cannot be cold. So those 3 have a membership value of 0 at this point. Similarly, we can define for slack, for low, for any motor speed, we can define the membership function and their membership term, fuzzy term. Okay, so we need to define rules so that we can kind of infer if what is the relationship between the input variables and the output variable. And for that, we, in this particular example, we have defined the 8 fuzzy rules that convert the input into their corresponding output fuzzy values. For example, the rule 1 simply states that if the temperature is hot and the fan motor speed is slack, then the flow rate should be high positive. If the temperature is hot and fan motor speed is low, then the flow rate is still high positive. If the temperature is hot and fan motor speed is medium, then the flow rate is positive. If the temperature is hot and fan motor speed is brisk, then the flow rate is high positive. So, excuse me. Yeah. So, this basically means that we can have a specific rule for any specific input value, any specific fuzzy value that is specified for the input variables. And here we see that this connects the input fuzzy logic values to the output fuzzy values. So let us define a fuzzy inference system. A fuzzy inference system is the key unit of a fuzzy logic system having decision making as its primary work. It simply uses the if-then rules along with connectors or and for drawing essential decision rules. The specific characteristics of a fuzzy inference system are that the output from an FIS is always a fuzzy set irrespective of its input, which can be fuzzy or crisp. It is necessary to have fuzzy output when it is used as a controller, and we are going to try to use a defuzzification unit along with the FIS to convert the fuzzy variables into crisp variables that are then usable for the output system. And hence, a fuzzy inference system is just the key unit of a fuzzy logic system that we are going to see in the next slides. So what are the functional blocks of FIS? There are 5 main components of FIS. The first component is the rule base. which contains the if-then rules, as we have seen earlier. The 8 rules, they define the rule base. Then you have got a database which defines the membership function of fuzzy sets used in fuzzy rules, and that is the membership function that we saw earlier before the fuzzy rule system that I have shown. The third unit is a decision making unit which performs the operations on rules to determine and make the decision. Then you need a fuzzification interface unit which converts the crisp quantities that are given at the input into fuzzy quantities that can be used by the rule base and by the database to make up the decision. Then you have got a defuzzification interface unit which basically converts the fuzzy quantities that are generated from the decision making unit into a crisp quantities that can then be used by the system to basically control or perform the function that is required. And hence these 5 main components make up the functional blocks of an FIS. Okay, moving on from fuzzy inference systems, we now talk about the fuzzy logic control system, of which fuzzy inference system is just a part. And the fuzzy logic control system is the main control system which is basically controlling the overall functioning of the machine, of the environment that we are trying to control. A control system by definition is an arrangement of physical components designed to alter another physical system so that this system exhibits certain desired characteristics. Fuzzy logic has been applied with great success in various control applications, and almost all the consumer products that we see today around us have some sort of fuzzy control inserted into them. So some of the examples from which you can identify the control systems are, for example, controlling room temperature with the help of an air conditioner. Again, you're trying to control the temperature. Similarly, another example is the anti-braking system used in vehicles, control on the traffic lights, washing machines, large economic systems, etc. And if you go by the reasons of using fuzzy logic in control systems, the main idea is that while applying traditional control systems, one needs to know about the model and the objective function formulated in precise terms. This makes it very difficult to apply in many practical cases where we cannot define things precisely, but a more fuzzy approach is required. By applying fuzzy logic for control, we utilize the human expertise and experience to design a controller which cannot be applied or utilized in the traditional systems for a few cases. The fuzzy control rules basically are simply just the if-else rules, and they are so simple that they can just be utilized in designing a controller, and they are not hard to implement at all. This is just the easiest thing to identify. And this defines the fuzzy logic control system. It's a control system that is based on the fuzzy inference system and is used to control the specific environment. There are 6 main assumptions when you are trying to design an FLC system. The first one is that a solution must exist. Of course, if a solution does not exist, then your FLC is going to be stuck, and it's going to fail for sure. So a solution must exist for each situation that has been given to the control system. Then the second thing is the range of precision, where the fuzzy logic controller must be designed within an acceptable range of precision. So you must define that within this precision we are going to work, and outside this it's going to be flawed. So you need to have a range of precision instead of just the exact precise value. Finally, the control engineering systems must look for good enough solutions rather than an optimal one. And a good enough solution is good enough for us. The fourth assumption in FLC design is the existence of a knowledge body, which states that there exists a knowledge body having linguistic rules and a set of input-output data set from which rules can be extracted and applied. The fifth assumption in FLC design is that the plant is observable and controllable. The input, output as well as the state variables are available for observation and controlling purpose. The sixth assumption is is the issues regarding stability and optimality. The issues of stability and optimality must be open in designing fuzzy logic controller rather than addressed explicitly. So with these 6 assumptions, we can kind of design an FLC system, and if all these properties, if all these assumptions are met by the controller system, then we can come up with a design for fuzzy logic controller system. And if any one of these is violated, you need to keep this in mind, then we cannot define or we cannot basically use fuzzy logic for in a control system. So to design a fuzzy logic control system, you must remember always first to verify that all these of 6 assumptions are met, and if all of them are met, only then can you proceed on with designing a fuzzy logic control system. Okay, so now we need to put in context what we have seen so far regarding the fuzzy controllers. In a fuzzy controller system, you've got a whole system which is basically a plant which has a sensor activated, and that sensor is going to get an input value for you that is going to sense what is happening in the environment and what is the expected input, and it will then define the error based on the readings from the sensor and what is the required input. It will feed that to the fuzzy controller, which takes in the crisp input, converts it into a fuzzy value by basically looking at the knowledge database. The input, this outputs the fuzzy value variable. The fuzzy linguistic variable is then input to the fuzzy inference rule system, which uses the rule base to infer how it should react to this particular input. And the output from the fuzzy inference rule is basically a fuzzy linguistic variable again. And this fuzzy value is defuzzified from the defuzzification unit and converted into a crisp output variable that is then fed back to the plant. The plant then feeds that to the sensor, and that sensor is basically just detecting the change that has happened in our control variable. The fuzzy controller system shown here is basically the fuzzy inference system, FIS, as we have seen earlier, while the whole system that is shown on this page is your fuzzy FLC control or FLC design system. And this whole thing, this whole controller is used in anti-braking systems, it's used in air conditioners, it's used in washing machines and all sorts of automatic control systems. So there are 5 main components of FLCs as well, and these 5 components are very similar to the ones that we have seen for FIS. So in that sense, there's no real difference between FLCs and FIS. But just to kind of give you a overview again of the major components of FIS, I'll just kind of go through the slide to talk about the same thing. You again have got a fuzzy fire, you have got a fuzzy knowledge base, you have got a fuzzy rule base, you have got an inference engine, and then you've got a defuzzifier. The fuzzy inference engine is basically the place where all the decisions are made, and this is the decision making unit. The fuzzy fire is just used to convert the crisp input into fuzzy value. The fuzzy knowledge base defines the relationship between input output fuzzy values, and it also contains the membership functions, which we have seen from the previous lecture, how useful they are and what do they depict. So the fuzzy knowledge base is the place which contains these things. Fuzzy rule base contains the rules for converting the fuzzy input into the fuzzy output, and this is the actual place that contains the knowledge about the operation of the process of domain. So for example, for air conditioner, what variables are important. For a room cooler, a different set of variables is important, and the relationship between them might differ as well. So this is the place. The fuzzy rule base is as I see it, is the place where your whole knowledge of the domain is really important and is used. In all other places, your knowledge of the domain is not used, but the fuzzy characteristics and fuzzy terminologies will be used. Then if you move on to the defuzzifier, that's the place that is going to defuzzify and convert your fuzzy output values into crisp values, so that they can be used by your plant for further processing. So in essence, as we see here, the major components of FLC are exactly the same as that of fuzzy inference systems. The only difference is FLC is basically a larger part that also contains FIS, and that extra things that are contained are just the sensors and maybe the input and the control. But those three are not really the components that are shown here, and in that sense, if you want to include them as well, then you've got 8 major components for FLCs. The first 5 are the same as that of FIS, while the other 3, which is basically the sensors, the plant, and maybe the input value and how you connect them, that portion is not shown here, and I will like to skip them as well for now. So another important thing is, how do you design an FLC? What are the important steps here? And we're going to see that I'll just kind of explain the steps here really, but in reality we are going to see the application of this particular part in the next lecture, section 9.4, which is going to talk about how we are going to actually design a system for a room cooler, and I'll follow all of these steps in that. But for the sake of explanation, for the sake of putting things out right here and defining them, we have basically identified 7 main steps for designing FLCs. The first step is the identification of variables, where the input, the output, and the state variables must be identified for the plant which is under consideration. And we'll see that, like in the cooler example that I gave earlier, we have identified the input, which is the 2 variables, fan speed and the temperature, and we defined the output as well, which is basically the water, the speed of the water motor, and so those are the 3 main variables that are interesting for us. So the first thing, of course, is to identify the variables. The second step is to configure the fuzzy subset, so that we define the universe of information, which is then divided into number of fuzzy subsets, where each subset is assigned to a linguistic label. For example, we saw that for example for temperature, we can have positive, we can have high, we can have high positive, we can have negative, we can have low negative, etc., etc. So those fuzzy subset configurations for each variable, getting a subset of fuzzy values or fuzzy terms for each subset, is what this step is concerned about. The third step is obtaining membership function. Of course, it's not just necessary to define the fuzzy terms, but also to define which temperature corresponds to which term for a given range of temperatures, and for a given range of variables you need to define it and do the same. And this particular thing where we are obtaining membership functions for each fuzzy subset is the third step for our designing of FLCs. In the fourth step, which is basically configuring the fuzzy rule base, we need to formulate the fuzzy rules by assigning relationships between fuzzy input and output, like we have done before, and I've shown the 8 fuzzy rules. That is my fuzzy rule base, and that is how I configure this. So this is up till step 4. We are just configuring our system, we are defining things, we are defining how system looks like, and we are going to use the information of the domain to define all of these steps. And from step 5 onwards, it's basically the actual functional body or the functional steps that are required, that are dependent on the input when it comes in. So the fifth step in designing of FLCs is that we need to fuzzify the given input and determine the fuzzy terms for the input values. And this fuzzification step is the part or is the step at which the actual working of the system begins. So this is the fuzzification step. Next, we need to combine the fuzzy outputs, and by applying fuzzy approximate reasoning, we need to locate the fuzzy output and merge them together to get a single output from them. So this is the decision making phase where we are going to combine the fuzzy inputs into a corresponding fuzzy output value. And finally, of course, we need to defuzzify this fuzzy output, this final value, and come up with a crisp output to give back to the system that the system can use for its own purpose. For example, in the case of water cooler, it's going to regulate the speed of the fan, and that is kind of the motor actually. So that's the kind of output that we want. So we want an exact speed at which the water motor should be pumping, and that exact speed is what the defuzzification unit is going to give to us. So combining all these steps together, we now can design an FLC, and this is exactly what I'm going to do in the next lecture for room water cooler. A natural question is, why do we want to use fuzzy logic control systems instead of the traditional PID or the logic, the systems that we have seen that are based on traditional logic or Boolean logic? Well, there are manifold advantages of fuzzy logic control systems, but here I've listed the six that apparently are the most important ones to me. First and most importantly, if you want to get the same performance from a traditional system and you want to get the same performance from an FLC based system, an FLC based system is to develop it's a much cheaper prospect than developing a model based or other controllers in terms of performance. The second important characteristic which differentiates an FLC from traditional PID controllers is the robustness of the system. FLCs are more robust because of their capability to cover a huge range of operating conditions. The third important benefit of using an FLC system is the customizability of an FLC. FLCs are customizable to a given set of problems and to a given set of conditions. Fourth important benefit or advantage of using FLCs is that they emulate human deductive thinking. Basically, the FLC is designed to emulate human deductive thinking, the process people use to infer conclusion from what they know. So to convert the knowledge to conclusion, FLCs actually follow the same or emulate the same human deductive thinking that humans usually do in their own practical lives. Then the fifth advantage of FLCs is that the FLC systems are more reliable than the conventional control systems, and this reliability and robustness is at the core of FLCs and why they are used in a lot of our applications these days. The sixth important characteristic that differentiates an FLC from traditional logic based systems is its efficiency. Fuzzy logic provides us more efficient and more efficiency when applied in control systems. So you need to keep this in mind that FLCs are not only cheaper, but they are also robust, customizable, reliable, efficient, and on top of that they emulate human deductive thinking, and that's why for us they seem more like more reasonable and more understandable than the traditional logic controllers. Of course, when we talk about the advantages of fuzzy logic control systems, there are certain drawbacks to fuzzy logic control systems as well. For example, to really understand the rules and regulations that are required for a system, we really need a lot of data for an FLC to be applied, and that is the harder part. That in a lot of systems there is not really a lot of times a lot of data is available, and this being based on a lot of data is kind of a necessity for a fuzzy logic control system to work, and that's a drawback. The second drawback is the usefulness in case of moderate historical data. Of course, FLC is not useful for programs much smaller or larger than the historical data, and that is one problem that is faced by FLCs. The third one is, of course, that for an FLC system to work, or the accuracy of the system is directly dependent on the knowledge and expertise of the human beings that are feeding that information to it. And that high human expertise in the domain where this FLC will be applied is kind of really expensive at times, as well as I would say that it would lead to a lot of problems if the human is lacks in a particular scenario or in a particular case. Then this lack of human expertise can come back to bite. And finally, of course, it needs regular updating of data and rules depending on how the conditions are changing, and we need to update the fuzzy logic rules with time. So these are the four major I think drawbacks that are associated with fuzzy logic control systems. But one feels like if you have got enough data and if you have got enough human expertise, then these should not be a problem to deal with. And hence I personally feel that the fuzzy logic control systems, and especially when you see the next lecture on section 9.4, you'll kind of also identify that they are very simple to apply, but at the same time you need to be wary of these requirements. And you'll see that they are the reason for their popularity is the 6 advantages that we have seen in the previous slide. So let us apply fuzziness in neural networks as well, and this is a really important aspect and a really interesting I would say research aspect of applying fuzziness in neural networks. So fuzzy logic is largely used to define the weights from fuzzy sets in neural networks, and that is where in fuzzy neural networks it's basically the weights that are defined in terms of fuzzy set, and this in particular is useful where it's not possible to apply crisp values for weights. Then in that case we can use the fuzzy values. The training and learning helps the neural networks to perform better in unexpected situations. At that time, fuzzy values would be more applicable than crisp values, of course, given the previous condition. When we use fuzzy logic in neural networks, then the values must not be crisp, and the processing can be done in parallel. So despite having numerous advantages, there is also some difficulty when we try to use fuzzy logic in neural networks. The difficulty is related with the membership rules. They need to build fuzzy system because it is sometimes complicated to deduce it with the given set of complex data. The take home message from this particular slide is that of course we can combine fuzzy logic in neural networks in the way that at least the first way would be that we use weights, and the term instead of using crisp values and or a specific weight, we actually use fuzzy terms to define the weights. Of course, the usefulness is that at times it is not possible to use the crisp values, and it's at that point that the fuzzy values become interesting. In particular, for unexpected situations, I think this training and learning with the fuzzy values or fuzzy terms really helps the neural network to perform better. That's again, if you want to use fuzzy logic into neural networks, then the input values must not be crisp. Of course, they should convert the fuzzy values to neural networks into fuzzy values, and or in such a case the processing can be done in parallel thanks to the neural network architecture. But the main problem is defining the membership rules for defining the crisp terms, or fuzzy terms, and this is sometimes complicated because we cannot convert a complex data into their corresponding fuzzy terms really easily, and that is the problem or the drawback that one faces when he wants to introduce fuzziness in neural networks. But still, it's a very important or a very popular application of fuzzy logic in neural networks. So, an alternative application of fuzzy logic and neural networks is to actually train the fuzzy logic using a neural network, and that's the reverse relationship that you have seen from earlier. So instead of incorporating fuzzy logic into a neural network, we are now going to incorporate a neural network into the fuzzy logic, and which is the reverse relationship between neural network and fuzzy logic. That is, neural network used to train fuzzy logic is also a good area of study. And the two major reasons to build neurally trained fuzzy logic is that new patterns of data can be learned easily with the help of neural networks. Of course, that's the strength of neural networks, to identify new patterns, and hence that can be used, this particular strength of neural networks can be used to pre-process data in a fuzzy system. Secondly, neural networks, because of its capability to learn new relationship with new input data, it can be used to define fuzzy rules to create fuzzy adaptive system. So the term fuzzy adaptive system is basically a term for a system in which the fuzzy rules are basically refined or adapted to the particular environment, and this can be done by using neural networks to update the fuzzy rules or refine the fuzzy rules. So these fields have been combined in a lot of different works, and I'm not going to go into details of the applications here, but a laboratory in Yokohama, Japan has derived fuzzy rules and used a backproportional neural network, and it has been successfully applied to foreign exchange trade systems with approximately 5,000 fuzzy rules to depict what is happening at the trade market. Similarly, Ford Motor Company has developed trainable fuzzy systems for automobile idle speed control. NewFuzz, a software product of National Semiconductor Corporation, supports the generation of fuzzy rules with a neural network for control applications. And similarly, AEG Corporation of Germany uses neural trained fuzzy control systems for its water and energy conserving machine. It is having a total of 157 fuzzy rules. So here is where you can see that the neural trained fuzzy logic has been applied to a lot of different fields of application, to a lot of different control systems, and they are working absolutely great by using the combination of neural networks and fuzzy logic. So now let's quickly summarize and find the key points for the current lecture. The fuzzy inference systems FIS form the backbone of fuzzy logic control systems FLCs. There are three main models that are used for conversion from crisp values to fuzzy terms of fuzzy inference processing: the Mamdani, the TSK, and there was another similar model that we have seen. A typical case study for controlling the speed of motor for room cooler was discussed in this lecture, where fuzzy regions, fuzzy terms, membership functions, and fuzzy rules were shown with examples. A fuzzy inference system and their functional blocks were shown. There were five main functional blocks that we saw for fuzzy inference systems. Then we moved on to fuzzy logic control systems, which were defined and applied, and different applications were given for FLCs. The assumptions in designing FLC systems were discussed along with flow diagram. The major steps in designing FLCs, that were 6, were discussed, and I told you that the actual example for this will be coming up in the next lecture. The advantages and disadvantages of using FLCs versus traditional controllers was discussed in detail. And finally, we actually saw how we can combine fuzzy logic and neural networks for an interesting research topic. And this can be done in two ways. Either we can use fuzzy logic to define the weights in neural networks and fuzzy terms, etc. Or the other way is that we can actually use neural networks to define fuzzy rules, and we basically saw some applications of these in real life as well. So with that, this lecture comes to an end. I think it was very important to discuss the complexities and the steps that are involved for designing a fuzzy inference system and a fuzzy control system, and we saw the basics and we saw the theory with which we can now develop our own system as well, and that is what we are going to exactly do in the next lecture. Okay then, see you in the next lecture. Take care. Allah Hafiz.